Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lectures on chapter 4. Let's go ahead and get started with problem number 1. Problem number 1 says, which of the following best describes ionic compounds? So just as a reminder, ionic compounds are formed from the electrostatic attraction between oppositely charged ions. These ions are usually produced when atoms of metals lose electrons to become positively charged cations, and atoms of nonmetals gain those electrons to become negatively charged anions. The strong attraction between these oppositely charged ions hold them together in a solid structure known as an ionic lattice. Keeping that in mind, let's read each option and work through it together. The first option says ionic compounds are formed from molecules containing two or more atoms. Now, this statement is incorrect. Ionic compounds are not formed from molecules. Instead, they consist of a large network of ions in a lattice structure. Molecules, those are typically associated with covalent compounds where atoms share electrons. Now, answer choice B says ionic compounds are formed of charged particles and are measured by molecular weight. Now, this is partially correct but misleading. Now, while ionic compounds are indeed formed of charged particles or ions, they're not measured by molecular weight. Instead, they're measured by formula units, and their mass is given in terms of formula mass, not molecular weight. And so here, A and B, rather than forming molecules or being measured by molecular weight, ionic compounds form large arrays of ions in crystalline solids, and they're measured with formula weights. Hence, again, why A and B here are incorrect, and we can go ahead and eliminate both of those options. All right, let's read option C. C says ionic compounds are formed of charged particles that share electrons equally. This statement is incorrect. Ionic compounds form through the transfer of electrons from one atom to another, not by sharing electrons. Sharing electrons equally is a characteristic of covalent bonds, not ionic bonds. So C is also incorrect. Let's read our last and final option. Option D says ionic compounds are 3D arrays of charged particles. This statement is correct. Ionic compounds form a three-dimensional lattice structure where each ion is surrounded by oppositely charged ions. And this lattice is a repeating array extending in 3 dimensions, characteristic of the solid state of ionic compounds. And so all in all, our correct answer is going to be D. 1 is D. Let's go ahead and move into problem 2. Problem 2 asks, which of the following compounds has a formula weight between 74 and 75 grams per mole? Now, formula weight is used for ionic compounds, whereas molecular weight is used for covalent compounds. Looking at our answer choices, B and D are both covalent compounds and thus are measured in molecular weights, not formula weights. So we can go ahead and eliminate both of those answer choices. B is butanol, we can go ahead and eliminate that. And D is boron trifluoride, also a covalent compound that we can eliminate. All we're left with is answer choice A and C. We have potassium chloride and magnesium chloride. Let's go ahead and figure out the formula weight for each and see which one is closer to that 74-75 grams per mole range. For A, potassium chloride, we're going to sum up the atomic weight for potassium and for chlorine. Potassium has an atomic weight of 39.1 grams per mole, and chlorine has an atomic weight of 35.45 grams per mole. Now we can round these numbers to make the addition easier. This is about 40 and this is about 35. 40 plus 35 equals 75 grams per mole. That's for potassium chloride. What about for magnesium chloride? Magnesium has an atomic weight of 24.31 grams per mole, and chlorine has an atomic weight of 35.45 grams per mole, and we have 2 chlorine atoms, so that is going to be multiplied by 2. Now we can do some approximating here. 24 can be rounded up to 25 plus 2 multiplied by 35. So what we have essentially here is 25 plus 70, which gets us 95 grams per mole. So we have 75 grams per mole for potassium chloride and 95 grams per mole for magnesium chloride. Which one of these compounds has a formula weight between 74 to 75 grams per mole? That is going to be potassium chloride. So the correct answer for problem 2 here is going to be A. Let's move on to problem 3. Problem 3 asks, which of the following is the gram equivalent weight of sulfuric acid with respect to protons? Now, the amount of a compound measured in grams that produces one equivalent of the particle of interest is called the gram equivalent weight, and it can be measured as the molar mass divided by N, where N is the number of particles of interest produced or consumed per molecule of the compound in the reaction. That means that the first thing that we have to do here is calculate the molar mass of sulfuric acid. So let's go ahead and do that. Here we have 2 hydrogen atoms. Each atom of hydrogen weighs 1.01 grams per mole. Then we have 1 sulfur atom. Sulfur has an atomic weight of 32.07 grams per mole. And then we have 4 oxygen atoms. Each oxygen atom has an atomic weight of 16 grams per mole. 2 times about 1 is 2, plus 1 times 32, we're going to keep that as 32, plus 4 times 16, which is 64. 2 plus 32 is 34. 34 plus 64 is equal to 98 grams per mole. Okay. So far, so good. Now, the next thing we have to do now that we figured out molar mass is figure out N. Sulfuric acid, H2SO4, this is a diprotic acid, meaning it can actually donate 2 protons per molecule. Now, the equivalent weight is going to be calculated here by dividing the molar mass by the number of protons it can donate. And so that's going to equal 98 grams per mole, because that's the molar mass of sulfuric acid, divided by 2, because that's the number of protons that sulfuric acid can donate. 98 divided by 2 is approximately 49. 49 grams per equivalent. And so that's what we're looking for our answer. If we look at the answer choices, that's going to be answer choice A. So problem 3 is A. Moving into problem 4. Problem 4 says which of the following molecules cannot be expressed by the empirical formula CH. A is benzene, and I went ahead and drew that for us. Benzene is drawn here. This is a 6-carbon ring with double bonds, and the molecular formula for benzene is C6H6. Answer choice B is ethine. This is drawn right here. It's a carbon-carbon triple bond, and then each carbon also has a hydrogen, and the molecular formula for this is C2H2. Then we're given this following structure. This is C3H4, and then D, we have the following structure, C8H8. Now we're asked which of the molecules cannot be expressed by the empirical formula CH. Now the definition of an empirical formula is a formula that represents a molecule with the simplest ratio in whole numbers of the elements comprising the compound. In this case, given the empirical formula CH, any molecule with carbon and hydrogen atoms in a 1-to-1 ratio would be accurately represented by this empirical formula. Looking at A, C6H6, if you divide each of these numbers by 6, you would get CH. So benzene can be represented by the empirical formula CH, and that's because the carbon and hydrogen atoms are present in a 1-to-1 ratio. If we look at B, C2H2, if we divide each number by 2, we would also get CH. And so again, this molecule can be expressed by the empirical formula CH. And again, it's because carbon and hydrogen atoms are present in a 1-to-1 ratio. C is C3H4. This cannot be simplified further. The molecular formula is the empirical formula. And you notice that the empirical formula is not CH. And that's because here, carbon and hydrogen are not present in a 1-to-1 ratio. C is actually our correct answer. This is the molecule that cannot be expressed by the empirical formula CH. But let's go over D as well. D is C8H8. If we divide each number by 8, we would get CH. And so this molecule can be expressed using the empirical formula CH. The only molecule that cannot is going to be molecule C. And so the correct answer to 4 is C. Let's move on to problem 5. Problem 5 says, in which of the following compounds is the percent composition of carbon by mass closest to 62%? Now, the percent composition by mass of any given element within a molecule is equal to the mass of that element in the molecule divided by the molar mass of the compound, all multiplied by 100%. So for each of these answer choices, we're going to have to figure out the mass of carbon and then divide that by the molar mass of the compound as a whole and multiply all of that by 100%. So for this first option, acetone, I have the molecule drawn right here. Here is the molecular formula for acetone, C3H6O. We have 3 carbon atoms at 12 grams per mole each. We have 6 hydrogens at about 1 gram per mole each, and 1 oxygen atom at about 16 grams per mole each. If we sum up 12 times 3, which is 36, plus 6 plus 16, we should get about 58 grams per mole. That is the molar mass of the compound. That's going to be our denominator. Our numerator is the mass of carbon alone. We have 3 carbon atoms at 12 grams per mole each. That's a total of 36. So that's going to be our numerator. 36 divided by 58 multiplied by 100%. This is going to be about 62% carbon. Let's do option B. Option B is ethanol. I have the molecule drawn right here, and here is the molecular formula. C2H6O. Here we have 2 carbon atoms at 12 grams per mole each. That's 24 grams per mole. That's our numerator. Then let's figure out the molar mass of the molecule as a whole. So from carbon, we have 24 grams per mole. We have 6 hydrogens at 1 gram per mole each. That's 6 grams per mole. And then we have 1 oxygen atom at 16 grams per mole. So 24 plus 6, that's 30, plus 16, that is 46. So that's going to be our denominator. 24 divided by 46 multiplied by 100%. We can approximate 24 to about 23. 23 divided by 46 is about 50%. If you put it in the calculator, it's about 52%. That's close enough here. So we have about 50% carbon. All right, what about answer choice C? That's propane. I have that drawn right here. The molecular formula is C3H8. We have 3 carbons at 12 grams per mole each. That's a total of 36 grams per mole. That's our numerator. And then we have 8 hydrogens to add to the 36. That's going to be 44. That's the total molar mass of the compound. That's going to be in our denominator. 36 divided by 44 multiplied by 100%. That's about 82% carbon. And then our last and final answer choice is methanol. I have that drawn here, and the molecular formula for methanol is CH4O. There's only 1 carbon atom here at 12 grams per mole. That's going to be our numerator. For our molar mass of the compound as a whole, we have 12 grams per mole for that one carbon, 4 grams per mole for the 4 hydrogens, each at 1 gram per mole, and then 16 grams per mole for the single oxygen atom we have. 12 plus 4 is 16. 16 plus 16 is 32 grams per mole. That's our denominator. 12 divided by 32 multiplied by 100% is going to be 38% carbon. Now that we have the percent composition of carbon by mass for each of our answer choices, we're going to look to see which one is closest to 62%. That's going to be for acetone. So the correct answer for problem 5 here is going to be answer choice A. Let's move on to problem 6. Problem 6 asks, what is the most specific characterization of the reaction shown? We have calcium hydroxide reacting with sulfuric acid to give us calcium sulfate and water. So what we're seeing here is an base reacting with an acid to give us salt and water. We also notice that there is an exchange of ions between the two compounds here, calcium hydroxide and sulfuric acid. We form calcium sulfate and then water. Keeping that in mind, let's go through the answer choices together. A says single displacement. Single displacement involves one element being displaced by another in a compound. This is not the case here. We see actually a double displacement. B says neutralization. Now, neutralization is a specific type of double displacement reaction where an acid reacts with a base to produce a salt and water. Calcium hydroxide is a base. Sulfuric acid is an acid, and they produce calcium sulfate, which is a salt, and water. This matches what we're given in our reaction and what is happening. We have a neutralization reaction. We see our double displacement. Neutralization is a specific type of double displacement, so this is the best characterization of the reaction that we're given. The correct answer is B. Now, C says double displacement, and while that is correct, neutralization is a more specific description of our reaction. Because yes, the double displacement is happening, but it's happening with an acid and a base to produce salt and water. D says oxidation reduction. This involves the transfer of electrons between two substances. There is no change in the oxidation states of the elements in this reaction. This is not an oxidation reduction reaction. And so, in short, to summarize, while the reaction can be classified as a double displacement reaction, it is more specifically a neutralization reaction because it involves an acid and a base producing salt and water. And so the correct answer for 6 is B. 7 says in the reaction shown, if 39.5 grams of sodium sulfide is reacted with 85.5 grams of silver nitrate, how much of the excess reagent will be left over once the reaction has gone to completion? In the reaction that we're given, we have 1 mole of sodium sulfide reacting with 2 moles of silver nitrate to give us silver sulfide and sodium nitrate, 2 moles of sodium nitrate. Let's go ahead and work through this problem to determine which is the excess reagent and what is the limiting reagent, and then how much of the excess reagent will be left over once the reaction has gone to completion. We're going to have to first figure out the moles of each reactant. And in order to do that, we're going to have to figure out the molar masses of each of our reactants. So our first reactant is sodium sulfide, Na2S. We have 2 sodium atoms. Each sodium has an atomic weight of about 23 grams per mole. And then we have 1 sulfur atom, and each sulfur atom has an atomic weight of 32.1 grams per mole. And so what we have here is 2 times 23, which is 46, plus about 32. That gives us 78 grams per mole for the molar mass of sodium sulfide. Okay, what about our other reactant, silver nitrate? we have one silver atom. Silver has an atomic weight of about 107.9 grams per mole. We have one nitrogen atom. Nitrogen has an atomic weight of 14 grams per mole. And then we have 3 oxygen atoms, each have an atomic weight of 16 grams per mole. So we have about 108 plus 14 plus 3 times 16, which is 48. Let's go ahead and add 108 plus 14. That is going to equal 122 plus 48. All right, this is going to give us 170 grams per mole. All right, so we have the molar mass for both of our reactants. Now we can figure out the moles of each reactant because we're given the initial masses and we know the molar mass. So that is going to be our second step. Figure out the number of moles. What is the initial mass of sodium sulfide that we were given? We were given 39.5 grams of sodium sulfide to begin with. We're going to multiply that by its molar mass to get the number of moles. The molar mass of sodium sulfide is 78 grams per 1 mole. We can think about this, right? We have 39.5 grams over 78 grams. That's approximately 40 over 80. That's about 1/2. So we have approximately 0.5 moles of sodium sulfide, right? We just approximated this to about 40. We approximated this to about 80. Essentially, we just have 40 over 80, which is 1/2, which is equal to 0.5. Just want to show you the math, just in case. Okay, what about our other reactant, all right? Silver nitrate. Our initial mass of silver nitrate is 85.5 grams. We're going to multiply that by the molar mass. For silver nitrate, it's about 170 grams per 1 mole. Again here, what you notice is we can round this to 85. We can round this to 170, keep it at 170. 85 over 170, that's again about 1/2. So 0.5 moles of silver nitrate. Now that we have the moles of each reactant, let's reference back our actual chemical reaction. This balanced equation we were given shows that we have 1 mole of sodium sulfide and it reacts with 2 moles of silver nitrate. So let's think about this. If we have, let's start off with this. If we have 0.5 moles of sodium sulfide, the amount of moles of silver nitrate that we would need is 0.5 multiplied by 2, since the ratio is 1 to 2, sodium sulfide to silver nitrate. So if we had 0.5 moles of sodium sulfide, we would need 1 mole of silver nitrate to react because we have a 1 to 2 ratio of sodium sulfide to silver nitrate. But we don't have that. We calculated 0.5 moles of sodium sulfide and only 0.5 moles of silver nitrate. That means that silver nitrate here is the limiting reagent. This is the limiting reagent. So that means we're going to use all 0.5 moles of silver nitrate. And that means we're only going to be using then 1/2 of our moles of sodium sulfide. We need to remember our 1 to 2 ratio. Okay? Since silver nitrate is our limiting reagent and we're going to be using all of it, all 0.5 moles of it, how much of our excess reagent will we actually use then? Just half, since we have a 1 to 2 ratio. And so we will only be using 0.25 moles of our excess reagent. If we're only using half of our moles of our excess reagent, that means that we're going to have half of it left. We're going to have 0.25 moles of sodium sulfide remaining. Let's figure out what that is in grams because that is what our problem is asking. It is asking for the mass of our excess reagent. We're just going to use our molar mass again to convert. 1 mole of sodium sulfide has a mass of 78 grams per mole. So there we have it. We've written it in fraction form. What we have here is 1/4 multiplied by 78 grams over 1 mole. Let's approximate 78 to 80 grams because 80 divided by 4 is an easy calculation. That's about 20 grams. What we have as excess reagent is 20 grams of sodium sulfide. If we look at our answer choices, the one that's closest to that is going to be answer choice A, 19.5 grams of sodium sulfide. And so the answer to 7 is A. This is very similar to a practice problem we did in lecture. Let's go ahead then and move to problem 8. Problem 8 says, using a given mass of potassium chlorate, how would one calculate the mass of oxygen produced in the following reaction, assuming it goes to completion? Now we're going to have to use stoichiometry based on the balanced chemical reaction here to accomplish this goal. Now what we're given to start off with is grams of potassium chlorate. The first thing that we're going to have to do is convert this mass into moles. And in order to do that, we're going to take the grams of potassium chlorate, we're going to divide it by the molar mass of potassium chlorate. So that's our first step, convert from mass to moles of potassium chlorate. Then the second step here is we're going to have to use the stoichiometric ratio from the balanced equation to convert moles of potassium chlorate to moles of oxygen gas. We get that from the balanced chemical equation. For 2 moles of potassium chlorate, we have 3 moles of oxygen gas. So we're going to use that relationship, that ratio right here. So 3 moles of O2 to 2 moles of potassium chlorate. Then the last and final step is we're going to have to convert the moles of oxygen, all right, to grams of oxygen. And we can do that by taking the moles of O2 and multiplying it by the molar mass of O2. Now, with those pieces in mind, let's just actually put it together. All right, so let's write this out, combining all the steps. We started off with grams of potassium chlorate. We're going to multiply it by the molar mass, so this is some grams multiplied by mole. And you're not going to see this in the answer choices, so we're just going to refer to this as molar mass. But keep in mind that's what it looks like, grams of potassium chlorate per moles of potassium chlorate. Then we're going to go from moles of potassium chlorate to moles of oxygen. That's what we want. And we're going to use the ratio that we got from the balanced equation. And we said that for 2 moles of potassium chlorate, we have 3 moles of oxygen gas. And then our last step is to then multiply by the molar mass of oxygen gas. So for 1 mole of O2, we have some grams of O2. So this is the molar mass of O2. All right, so keeping that in mind, let's go ahead and try to find which one of these answer choices has the correct setup. The first answer choice, we have grams of potassium chlorate consumed. That's what we're given. That's correct. It will be in the numerator. And then we're going to have molar mass of potassium chloride in the denominator. This is going to be correct. We are essentially dividing by molar mass here because what we have is moles per gram. We're dividing by molar mass. So far, so good. Then we multiply it by the ratio that we get from the balanced equation. 3 moles of O2 in the numerator, 2 moles of potassium chlorate in the denominator. That's correct. We have all of that. That checks out. And then we multiply by the molar mass of oxygen gas, grams per mole. That means that we want to look for molar mass of O2 in the numerator, which is exactly what answer choice A has. And so answer choice A is actually the correct answer. If we look through the other answer choices, we notice that answer choice B doesn't have right off the bat the ratio that we want that helps us convert from grams and moles of potassium chlorate to moles of oxygen gas. We should have this 3:2 ratio of O2 to potassium chlorate that we don't even see in option B or option C for that matter. In option D, we have this division by molar mass of oxygen as well, and that's incorrect. And so the correct answer for 8 here is going to be answer choice A. Let's move into problem 9. Problem 9 says aluminum metal can be used to remove tarnish from silver when the two solid metals are placed in water according to the following reaction. The reaction is a blank. Is it a double displacement, single displacement, oxidation reduction reaction, or a combination reaction? So again, let's work through this answer choice by answer choice. We have 4 options. It can be more than one. Based off of our answer choices here, we can tell that maybe it can only be one of these 4 options, or it can be a combination of a couple. Let's look at our reaction. All right, we have the following reaction. We have aluminum metal reacting with silver oxide, and that gives us silver and aluminum oxide. Okay, in this reaction, there is a single displacement with the silver and silver oxide being replaced by the aluminum to form aluminum oxide. This single displacement reaction also necessitates a transfer of electrons in an oxidation reduction reaction. Silver, for example, it changes from the +2 oxidation state to a neutral state, all right, to a 0 oxidation state. Therefore, also aluminum changes from neutral to a +3 oxidation state. And so in this reaction, we see single displacement and we see oxidation reduction reactions. So statements 2 and 3 are correct. And the correct answer then for problem 9 is going to be D. Now, oxidation reduction reactions is something we'll further elaborate on in the appropriate chapter. So if this is something you do not remember from your general chemistry class, that's okay. Let's review it in our oxidation reduction lecture and then come back to this problem again, make sure we understand it once more. With that, we're going to move into problem 10. Problem 10 says, which of the following types of reactions generally have the same number of reactants and products? Double displacement reactions, single displacement reactions, and combination reactions. So let's talk about the general form for each, starting off with double displacement. In a double displacement reaction, elements from 2 different compounds swap places with each other to form 2 new compounds. And the general form for a double displacement is AB, reactant AB plus reactant CD, give us products AD plus CB. All right, now what you notice here in this reaction type, it typically involves 2 reactants and 2 products. Hence, the number of reactants is equal to the number of products. This falls under the category of reaction types that generally have the same number of reactants and products. What about single displacement reactions? A single displacement reaction occurs when an atom or an ion in a compound is replaced by an atom or ion of another element. It generally has the form reactant A plus reactant BC gives us product AC plus B. This reaction type involves usually 1 element and 1 compound as a reactant, producing 1 new element and 1 new compound. And so the number of reactants is equal to the number of products. This is also a type of reaction that generally has the same number of reactants and products. What about combination reactions? A combination reaction has 2 or more reactants forming 1 product, and the general form is usually reactant A plus reactant B give us product AB. right? This reaction typically involves 2 or more reactants combining to form one product. The number of reactants usually does not equal the number of products here. So this doesn't fall under our list of reactions that generally have the same number of reactants and products. That means only statement 1 and 2 are true, and that makes the correct answer for problem 10 to be C. Fantastic. Let's move on to problem 11. Problem 11 asks, diethyl zinc is a very unstable compound. When exposed to air, it reacts with oxygen to produce zinc oxide, carbon dioxide, and water. The unbalanced reaction is shown here. What is the coefficient for carbon dioxide in the balanced reaction? All right, so let's go ahead and begin to balance this reaction. Let's just quickly count the number of each type of atoms on both sides of the equation as is. If we look at the reactant side, we have 1 zinc atom. If we look at the product side, we have 1 zinc atom. All right, what about carbon? We have 4 carbons on the reactant side, 1 carbon on the product side. We have 10 hydrogens on the reactant side, 2 hydrogens on the product side. And then we have 2 oxygens on the reactant side and 1, 2, 4 oxygens on the product side. Let's go ahead and start to balance this reaction, starting off with carbon. Zinc seems to be balanced right now, so let's ignore that. Let's start with carbon. We have 4 carbons on the reactant side, all right, and we have only 1 carbon on the product side. So let's go ahead and add a 4 in front of this carbon dioxide here. So now the carbons match on both sides. Okay, so zinc so far, there's 1 on each side. Beautiful. Carbons, 4 on both sides. So far, so good. What about hydrogens? On the reactant side, we have 10. On the product side, we only have 2. So let's go ahead and add a coefficient of 5 right there so that we have 10 hydrogens on both sides. All right, now let's move on to oxygen. We said we have 2 oxygens on the reactant side. How many oxygens do we have on the product side? 1, 2, 3, 4. We have 4 oxygens on the product side. Let's go ahead and put a 2 in front of this reactant, O2. And now we have 4 oxygens on the reactant side as well. Everything is now balanced. Now the question asks, what is the coefficient for carbon dioxide in the balanced reaction? Well, we just have to look. We put a 4 right there. And so the answer is going to be A. 11 is A. Wonderful. 12. 12 says, in the process of photosynthesis, carbon dioxide and water with energy combine to form glucose and oxygen according to the following equation. What is the theoretical yield of glucose if 30 grams of water are reacted with excess carbon dioxide and energy according to the equation above? Now, whenever you're given an equation and it doesn't tell you that it's balanced in the word problem, then you want to double check and see if it is balanced or unbalanced. Here, this reaction is unbalanced. So the first thing we're going to have to do is actually balance this reaction. So let's begin that. Let's look at carbon first. On the reactant side, we have 1 carbon atom. On the product side, we have 6 carbon atoms. So we're going to go ahead and add a coefficient of 6 here to make sure that now the carbons are balanced on both the reactant and product side. Fantastic. Let's balance hydrogen next. On the reactant side, we have 2 hydrogens. On the product side, we have 12 hydrogens. So we're going to go ahead and add a coefficient of 6 right here to make sure that the hydrogens are balanced on both the reactant and product side. Now we're left with oxygen. On the reactant side, we have 12 plus 6 oxygens. We have a total of 18 oxygens. And on the product side, we have a total of 8 oxygens. 6 here in glucose, 2 over here. Now, if we ignore the 6, we're not going to play with glucose. What if we just focus on O2? What coefficient can we add here? So that number plus 6 adds up to 18. Well, if we put a coefficient of 6 right here, then we have 12 plus 6, and that gives us 18. So we're going to leave a coefficient of 6 right here. And now we've balanced the reaction. So let's go ahead and erase all our work, add in the coefficients, and move on to the second part of this problem, which is trying to figure out the theoretical yield of glucose if we have 30 grams of water reacting with excess carbon dioxide. So we have a 6 here, a 6 here, and a 6 here. Now this is just going to become a kind of stoichiometry problem. We're given that we have 30 grams of water to begin with. We want to figure out the theoretical yield of glucose. So here, we're going to use the stoichiometry, all right, from this balanced chemical equation to figure that out. The first thing we're going to want to do is convert grams of water to moles of water. Water is 18 grams per 1 mole of water. Next, all we have to do here in this next part is use our coefficients to our advantage. In this reaction, we have 6 moles of water to 1 mole of glucose. So that is the mole-to-mole ratio we're going to use here. 6 moles of water to 1 mole of glucose, C6H12O6. Then our last step is to use the molar mass of glucose to go from moles of glucose to grams of glucose, and that value is going to be our theoretical yield. Now here, we didn't calculate our molar mass, so let's do that together. We have 6 carbons at 12 grams per mole each, 12 hydrogens, 1 gram per mole each, and 6 oxygens at 16 grams per mole each. So 6 times 12 is 72, plus 12 plus 6 multiplied by 16. 6 multiplied by 16 is equal to 96. Okay, let's add up these first. 72 plus 12 is 84, and then add 96 to that. That is essentially going to be 180. So our molar mass for glucose is 180 grams per mole. Wonderful. Now, let's go ahead and calculate this out. Let's make a couple of approximations here. We're going to keep 30 as is, multiplied by 1 over, let's do 20, multiplied by 1 over 6, multiplied by 180 over 1. Okay, fantastic. Let's do some simplifications. We can cross out this 6 and divide this by 6 as well to have 5 right here. Then we have 5 over 20. We can further simplify that to 4. Essentially, what we're left with is 180 over 4. This is not too bad of a calculation. This is, if we approximate the top to be 200 now over 4, about 50 grams. We have about 50 grams of glucose produced. That is our theoretical yield. That means the correct answer here is going to be answer choice B. The answer to 12 is B. Wonderful. Let's move on to problem 13. Problem 13 says in the following reaction, we have gold 3 sulfide reacting with hydrogen gas to give us gold and hydrogen sulfide. Now, if 2 moles of gold 3 sulfide is reacted with 5 moles of hydrogen gas, what is the limiting reagent? Now, the first thing we have to do is we're given this reaction, we're not told it's balanced, so we would have to check if it is balanced or not before we start our work. And in fact, it isn't balanced. So let's do that first. Let's start off with gold. We have 2 gold atoms on the reactant side, but only 1 on the product side. So we're going to add a coefficient of 2 right here to make sure that it is balanced. Then we have sulfur. We have 3 on the reactant side and just 1 on the product side. So I'm going to add a coefficient of 3 right here to make sure that that is balanced. Then last but not least, we have hydrogen, 2 on the reactant side, and 6 on the product side. Now to make sure that's balanced, we're going to add a coefficient of 3 right here to get 6 hydrogens on the reactant side, just like we have it on the product side. Wonderful. Now this reaction is balanced and we can begin to do the work to answer this problem. Now we're given some interesting information. We're said if we have 2 moles of gold 3 sulfide and we have 5 moles of hydrogen gas, what is the limiting reagent? Now from the balanced equation, we see that for 1 mole of gold 3 sulfide, all right, it reacts with 3 moles of hydrogen gas. Therefore, 2 moles of gold 3 sulfide is going to require 6 moles of hydrogen gas, just based off of this ratio that we can get from the balanced equation. But we don't have 6 moles of hydrogen gas available. They're telling us we only have 5 moles. That means that our limiting reagent is going to be hydrogen gas. And that is because there isn't enough to fully react with the 2 moles of gold 3 sulfide that we have. And so the correct answer here for problem 13 is going to be B. Let's move on to problem 14. Problem 14 asks, which of the following would make the strongest electrolytic solution? Now, as a reminder, the best electrolytes, they dissociate readily, they have a high dissociation constant, and they're typically ionic compounds with large amounts of cations and anions. Let's go ahead and read through our options and work through them. A says a nonpolar covalent compound with significant solubility. B says an ionic compound composed of 1 cation with a +3 charge and 3 anions with a -1 charge. C says a polar covalent compound with a small dissociation constant. And D says an ionic compound composed of 2 cations with a +1 charge and 1 anion with a -2 charge. Now, looking at A and C, both of these would not make the strongest electrolytic solutions. A, we're dealing with a nonpolar covalent compound. Nonpolar covalent compounds do not dissociate into ions in solution. And then C says a polar compound with a small dissociation constant. A small dissociation constant indicates that the compound is a weak electrolyte. So then we're left with options B and D. Now for option B, this compound is going to dissociate into multiple ions. You're going to have 1 ion, all right, a cation that has a 3+ charge, and then you're going to have 3 anions with a -1 charge. And in D, you're going to have 1 cation with 2 cations with a +1 charge and 1 anion with a -2 charge. Now, considering this, the strongest electrolytic solution is going to be formed by the compound that dissociates into the most ions. Therefore, the ionic compound composed of 1 cation with a +3 charge and 3 anions with a -1 charge is going to produce more ions in solution than option D. Therefore, the correct answer for problem 14 is B. Let's move on to our last and final question, problem 15. Problem 15 says carbon disulfide and nitrous oxide, when ignited, react exothermically to produce elemental sulfur, nitrogen, and carbon dioxide. Since this reaction produces a woof sound, it is sometimes referred to as the barking dog reaction. Which of the following represents the balanced chemical reaction? Now, looking at the answer choices, we have the same reactants and products in all 4 options. So we're just going to go ahead and write out the reaction. All right. N2O plus CS2 gives us S8 plus CO2 plus N2. And we're going to go ahead and balance this reaction ourselves and then find the option that has the same coefficients as we determined. Let's start with sulfur. We have 2 sulfur atoms in the reactant side. We have 8 on the product side. So we're going to add a coefficient of 4 right here to make sure that it is balanced. Then let's move into carbon. On the reactant side, we have 4 carbons. On the product side, we only have 1. So we're going to add a coefficient of 4 right here to make sure that it is balanced. So now sulfur and carbon are balanced. Let's move on to oxygen. On the reactant side, we have 1 oxygen. On the product side, we have 8 oxygen atoms. So to balance this, we're going to add a coefficient of 8 right here, and now oxygen is balanced. Now we're going to do our last and final atom, which is nitrogen. On the reactant side, we have 16 nitrogen atoms. On the product side, we only have 2. We're going to add a coefficient of 8 right here, and lo and behold, nitrogen is now balanced. Everything is balanced, and the coefficients we have are 8, 4, 1, 4, 8. So that's what we're looking for. 8, 4, 1, 4, 8. And look at that. That is answer choice A. So the correct answer for 15 is A. And there you have it. We've completed this practice problem set. I hope that it was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.